G'day, my name is Brendan Gregg. I work at Netflix as a senior performance architect. And in this talk, I'd like to cover a dream I realized when I began work at Netflix. And that was to understand CPU usage for Java quickly and completely. Quickly. We have an open source GUI we're developing called Vector, and that's a screenshot. If we see utilization is high for an instance on our cloud, I want to be able to click a button and have it completely tell me why. Break down that CPU utilization into the components. In this talk, I'm not going to cover Vector, although it is open source and you can use it. I will talk about the commands you can use after you've logged in via SSH. And a lot of companies have their own GUIs for monitoring and doing analysis. Since these are just Linux commands, you can copy them and script them and fold them into your own GUIs. Or you can use Netflix Vector. So I'm not actually selling any products, just these open source tools that many of us have been working on and developing. Completely means I want to see all CPU cycles. So whether it's in Java, running Java methods, in the JVM code itself, in C++, whether I'm doing GC and exactly how I'm doing GC, or whether I'm in the kernel. And I want to see all of those CPU cycles proportionally together in one visualization so that I can compare them and make decisions about where tuning efforts are best spent. We have this fallacy where the bugs seem greatest in the code that you work on yourself. And sometimes when I tell Java developers, I'll give you a visualization where you can look at not just Java, but you can also look at the kernel. And you can look at libc, and you can look at other system libraries. Sometimes the instinct is to say, those must be immaculate. That code must be perfect. Why would I want to look at the kernel's internal performance? I'm sure the kernel engineers are really smart engineers, and they've got it all sussed out. The problem is clearly my Java application. I've worked on kernel engineering performance for over a decade, and I have a different bias. For me, if there's a given performance issue, it's got to be the kernel. The kernel's just a mess. There's bugs everywhere. I'm sure the Java applications people are writing are immaculate, but I know the bugs in the kernel and the system libraries. It doesn't matter which kernel, whether it's Linux or OS X or Solaris, all software has bugs. So it depends on your bias. You do want to have a look at everything. Everything's on the table. I call this the messy house fallacy. It's when, if I invite someone around to my house, I have to warn them and say, I have to warn you, my house is a total mess. Because I assume your house is immaculate. If I go around to your house, it will be perfect. If I visit their house is a mess too. It's this bias I have because you live in your own mess. So we live in the code bases in front of us, but that's not the only area that can cause performance issues. So we do want to look at all of it. For some quick background and context, I work at Netflix. We have over 60 million subscribers, and we just launched in Spain. We have tens of thousands of instances on the Amazon EC2 cloud running Linux, Ubuntu. We have our own CDN, Content Delivery Network. That's the Open Connect appliances. They're running FreeBSD. It's also an awesome place to work. I can really recommend it. You can talk to me and Diane if that's interesting to you. The cloud I mentioned, it's on AWS EC2. And the standard programming environment we're using at Netflix is based on Java. Netflix itself is composed of many different microservices and applications. And there are some applications that are trying Node.js. And for all I know, there could be others trying other languages, but predominantly it's Java. And I've drawn a diagram there to give you an idea of what's running on our instances, all sorts of things. We want CPU profiling in particular for some many obvious reasons, to identify tuning targets, incident response, non-regression testing, and so on. But also, if you're new to the cloud, and especially auto-scaling groups, the way Netflix works is throughout the day, we will scale up and down based on load. And so we can add tens of thousands of instances during peak time and then reduce them quickly later, which is one of the awesome things about the cloud. That scaling is automated by metrics, which are often but not always, often CPU based. So the CPU consumption of your application directly automates how many instances we're going to launch over the next hour and the next week, and that directly affects our cost. So in the cloud, if we can identify a CPU performance win, even if it's 1% or 5%, we can realize that performance win immediately. Because next time we scale up for the auto scaling group, we will be 1% fewer instances out of tens of thousands. So it's cost savings as well, and these are cost savings we get to experience immediately. The problem with profilers. So there are lots and lots of profilers out there, and there are many profilers for Java. And I've drawn a visual representation of what I think when I use a Java profiler. With the Java profile, I've just masked the original flame graph I had on the title slide. With a Java profiler, I can't see the kernel, and I can't see libraries, and I can't see the JVM. When you're running as Java as a user-level process, you can't break outside of that and start inspecting bare metal and kernel and other areas. You need to do that via syscalls. So a Java profiler, like a JVM-TI profiler, can see itself. Usually you have some idea about GC. You've got a GC log. You've got other instrumentation as well. Java profilers, so Java method execution, we can see that. We can see object usage, nice heap profilers, GC logs, and usually some advanced custom Java context depending on the Java observability tool. Typical problems. It depends on the profiler, but many of them have sampling issues where the profile is skewed because they're sampling based on safety or yield points. Method tracing, where you're instrumenting every single method call, has serious observer effect. And if you read the documentation for these profilers, they'll confess that your app may run 5 times slower or 50 times slower if you turn this on. So generally use sampling. We take snapshots. Many of them misidentify running is on CPU. And so you see on Stack Overflow, all of these people complaining, ePOL is burning CPU on my Linux Java instance. No, it's not. Java doesn't know what's running on CPU. From Java's notion, it's in its running state. Java has its own thread states. But the kernel has ripped you off. You're blocked on a resource. So it can get confused about that. Some of the profilers have come up with workarounds, these band-aids where they patch these functions we know get confused, so don't treat them as CPU time, which is kind of awful. It doesn't include or profile GC or JVM time, we know that. And many of these profilers, they use these tree views where you click on the start of the thread and you can expand down the methods. They're okay, but I find them cumbersome and slow to use. So in general, Java profilers are inaccurate and incomplete. Now, that's not to say they haven't solved lots of problems. They have solved lots of problems, and I've used them to solve problems. But we can do better. System profilers, if the kernel is in control, well, that's great. The kernel can asynchronously interrupt anything. But the kernel can't see Java. Java gets JIT compiled, and the kernel doesn't understand how to walk through Java context. So you get to see everything but Java, which is really annoying. And the problems specifically on x86 are the kernel can't walk stack traces, and symbols are missing for Java methods. It's a little bit different on other architectures. Spark, you may at least have some stack traces working, but you may not have the symbols. It depends what the C2 compiler is doing with that frame pointer register. As a workaround, and something I did not long after I started at Netflix was, let's just use both. So we can run a Java profiler, like I don't mind the Google lightweight Java profiler. It's pretty easy to set up, it's open source. And we can use a system profiler, like Linux perf-events. You can generate a flame graph for each, and then at least you have 100% coverage. They're not together, but you have a greater visibility of issues. It was okay, and it was an improvement, but it was really frustrating to be looking at the kernel, the towers of time in kernel or locks, and not have the Java context. I really need this combined, unified. And so that's what the solution is, a Java mixed mode flame graph where the kernel can walk Java stacks as well and pull out all the method information. So the solution was to fix system profiling. You can't really fix Java profiling. because it's running as a user-level process. In fact, the way to fix Java profiling is you get Java to call into the kernel and get it to do it, at which point it's using a system profiler. It's the only way it's going to get the privilege to asynchronously interrupt everything. Visibility, once you fix the system profilers, is everything. So Java methods, JVM, GC, and so on. With the current implementation, and we may make this better, there are a couple of problems. It's not perfect. The way for x86 we've re-enabled the frame pointers, it was an optimization that made sense a long time ago, but nowadays it doesn't make that much sense. But you still may lose a tiny bit of performance. And when we're doing symbol dumps, it can consume a burst of CPU. So we end up with complete and accurate asynchronous profiling. Instead of having major issues, there's more minor issues, and it's a much more powerful tool to use. As a simple example, this is one of the first things we did when we just hooked up flame graphs with vector so we could see CPUs are hot and then click a button. This was a Netflix issue where an instance was burning 100% CPU. So you run top, you see Java's on CPU 100% of the time. It wasn't very responsive. Now at this point, the developer would likely just kill the instance and let our framework automatically generate another one. But since it's hot on CPU, let's just have a quick look at a flame graph and find out what it's doing. The flame graph has no green in it, and I was coloring Java methods as green. It just has this yellow stuff, which is the JVM. And it turns out that instance was stuck in the compiler. So we've got compile broker, C2 compiler, compile optimize, phase macro expand, process users and allocation. Who understands this stuff in the room? Oh, excellent, good. We might have some questions for you guys later. So I didn't understand this stuff when I first looked at it, but I can do an internet search for this stuff and quickly found that this was a known bug. And so that was actually pretty useful to what we'd normally have just terminated the instance, just to plug that stuff into an internet search and say, oh, it's this bug, it's fixed in this JDK level, we just need to go to this one. That's an example of a system issue where you may assume the problem is in your Java code, but actually the problem is in the compiler. Here's another one. This flame graph shows where have time is spent in exception handling. And I just want to zoom in on this one. I think it's a nice one. So I haven't covered the flame graph, like what they are yet. I want to dive in by showing you some of the outputs. But this is a complete profile of Java. It is a Tomcat benchmark that we were doing early this year to evaluate Tomcat versus RxNetty. And if I navigate around the flame graphs are interactive sfigs. I can mouse over, it tells me how much CPU time is in each area, and it's also proportional. I can click to zoom, so let me just click on this guy. There we go. And so once we get into that, so HTTP connection base, is stale, fill input buffer, socket read. So in socket read, we're actually spending CPU time doing exceptions, throw message, do a new exception. I imagine it's bundling up the information. If it does an exception, this is the stack trace it will print out. It actually calls back into Java again. So we go back and run a couple of Java methods. And then we go back into system code, back into the JVM. Really interesting stuff. What's nice about this is this ended up being, so this is throw message. Let me just zoom back out. I talked to the developers about it. It's like, oh, we're spending some time in throw message. I can use a feature of flame graphs and just search. And it will highlight all of the paths that have that text. So just search for throw message. And on the bottom right, I print it's a little small, but the percentage that was matched. And so throw message was matched in 8.6% of the profiles. So I quickly navigate this, and if I see something interesting and I say, hey, we should turn off the exception handling in this because we're not using it, well, if we turn it off, we'll get 8.6% faster because we will not be burning 8.6% CPU cycles. I can search for anything. This is Tomcat, Apache. quickly navigate and figure out where, like, especially if you're trying to figure out what does my code look like versus the profile, or someone has a hypothesis that, I'm not finding those guys, hypothesis that maybe, we're burning time in compression or encryption, and just quickly search for it, and it'll add it all up and then tell you the total percentage of the profile. So, and of course you can zoom around and navigate and really learn a lot about the system and how Java is calling in and out of the kernel. It's awesome stuff. Another quick example, this one was from last week. So the application developer wanted to rewrite the app because it was creating and destroying threads really quickly, and the assumption was this was burning CPU time, and this was inefficient. I was like, hold on, let's just have a look at a flame graph to see how much time is spent on thread creation and destruction. I blurred this a little bit because it's all of Netflix's internal code, but this is the production flame graph. And we navigated around this, and we found the thread creation and destruction from these thin little guys. And so the answer was, it's not actually worth the engineering time to re-architect the app for this problem, because this problem doesn't exist. So we were able to quickly exonerate the problem and come up and quantify it. Of course, since you see everything, you can actually look inside GC. So I know we have some C2 compiler experts in the room. What about GC experts? Anyone understand, once we're getting into card table mod, refbs, hard root scan with barrier to gens collection, anyone understand this stuff? All right, some people, good. So I need to do more work on this. I find it really interesting, but you get to see internally how GC is operating. GC is configurable. There's all sorts of different GC modes and algorithms you can use. See how it's operating on CPU. So those are a few quick examples. Now to give you the real background, CPU profiling is where we want to come up with an understanding of what the CPUs are doing by taking samples at a timed interval, plus some jitter. So let's say method A called method B to the syscall blocked, and then it returned. I might be waking up every 10 milliseconds or so and capturing a stack trace. So there's my stack A called B, and then when we're blocked, we're not capturing stack traces. And so if I wake up, if I do an interrupt that wakes up every 10 milliseconds and I gather these, and then I visualize them in a flame graph or a tree view or however, I come up with a pretty reasonable profile of what the CPUs are doing. I think a lot of us are familiar with what stack traces are, so this is an example from JStack. So you can read it bottom up or top down. So I started at main and I then called func A, func B, func C, or I can go top down and look at parents and grandparents. Stack traces are core of what we're doing for CPU profiling, because we're gathering these stack traces hundreds of times a second, or say 99 times a second on each CPU. This is not the same as, say, using the JStack tool. I should have noted that. I wouldn't run JStack 100 times a second. I don't think my application would make forward progress, because JStack is really invasive. JStack is invasive because it does all sorts of extra work and uninlines things. I'm using a system profiler that just walks the frame pointers, which is really not invasive. So system profilers that can do this, there's Linux, perf-events, which I'll use as an example. Oracle Solaris has dtrace, which is also a decent system profiler. OS X has instruments, Windows has xperf, and there are many others. Using Linux perf-events as the example, it provides the perf command, and a lot of people call it perf. I try not to call it perf because if you do an internet search for perf, it's really hard to find anything at all. So I try and make myself call it perf events so you can search for it. If you don't have it, it's usually easy to add. It gives you things like timer-based sampling, hardware events, trace points, and dynamic tracing. Hands up, who in the room is actually deployed on Linux? Okay, so it looks pretty much like well over 95%. So if you're on Linux, this is the official profiler. I know there are many profilers for Linux. This one is actually in the Linux source code under tools/perf. It can also do hardware events. It's really good at that. So it's good at things like level 1 cache misses and stall cycles and whatnot. Trace points from the kernel, and then dynamic tracing, both user and kernel. You can sample stack traces of almost everything on CPU. It's basically 100% of the time. Because I know too much about computers, I have to note that it is not 100% of the time, because sometimes it may not be able to sample a hard interrupt or an interrupt service routine running at a higher priority, in which case I've developed other tools that can solve that, which can then add it to the profile. But I've not actually had the need, because hard interrupts consume nearly 0% CPU, because they're designed to be really fast. So, if you ever have a problem with hard interrupts melting down the computer, you can observe that on Linux. I'd be surprised. But the greater point I should say, Linux can observe everything. Linux perf events gets you 99.999% of the way there. It's pretty easy to use the command line. Here's a typical invocation. Perf record, the frequency is 99 Hertz, and it will do that on all CPUs, is what A is for. And G means capture call graphs, where it'll walk the stack trace, for 30 seconds. Sounds like a lot of samples, and it is, but the way it's sampling them has been optimized. It's really fast. Yes?
What's with the 99?
Why 99? Because I don't want to sample, this is a good question, I should have had it. I don't want to sample in lockstep with some other activity and then oversample or undersample.
So you want to stagger it with other kind of repetitive activities happening on the same timer?
Yeah, I want to stagger it so that it doesn't sample in lockstep with another repetitive activity. If you're, has anyone done like a 10 millisecond loop to like poll something in your Java code? Sure, and if I sample at 100 Hertz, I might accidentally coincide like constructive interference with every single time your application wakes up, and then the profile will be skewed. Or destructive interference, where I miss it all the time and the profile is lacking. So you just wanted to have some jitter, so it's, I kind of want 100 Hertz, but I don't want 100 exactly, in case I collide with someone else's timer.
So given the natural kind of clock jitter, is that an actual problem in practical application?
It is a problem because timers are really fast these days. A few years ago I did answer that question by putting it to the test, and timers can be really accurate on CPUs. So we do want to kind of, in fact perf does have, if you go and use perf PMCs, it has some built-in jitter support. I think SystemTap does as well. So some of these profiles, you could say profile at 100 Hertz plus jitter, and it will handle the jitter for you. Here I'm explicitly typing the jitter. What a lot of information about 99 Hertz. But yes, these days I do it without even thinking. So this is going to, at 99 Hertz on all CPUs for 30 seconds, gather the stack trace. The way perf works is it dumps it to a file, perf.data, and then you post-process that. I use perf script, which just dumps out the samples. There's one stack sample, and it was a profile of bash. 47,000 lines were truncated because there's a lot of output. Perf has another mode, perf report, where it will condense and aggregate common code paths just to make the output less, so you don't have to read every single stack sample. It improves it a little bit, but here we've got 13,000 lines just for my quick test. And code gets more and more complicated, especially if you're profiling Java, and reading the perf report outputs becomes onerous and difficult. And that's where visualizations come in, like flame graphs. So that output, visualized, looks like this. So the screenshot is up in the top left-hand corner of the screen. That's all of the text from just one example of Linux perf report. I have even worse examples where it just looks like gray, like a gray box. There's just so much text. And it seems funny, but when you're the performance engineer and you have to understand this really quickly to debug a live issue, it's annoying. That's a flame graph visualization of the same data. So everything is on the screen, and I can read where the bulk of the samples are. So with flame graphs, on the y-axis is the stack depth. So at the bottom, There's where my threads start, and then I can see it stacking through code. The top edge is what's running on CPU. The color, in this example, is just random. It's not that important. And the x-axis is merely the population. So the x-axis is not passage of time, which confuses a lot of people, because many visualizations show the passage of time on the x-axis. Try it. I tried it with stack samples, and it just becomes a great big mess. Because if you're sampling at, say, 10 milliseconds, stacks can change dramatically every single sample. And so if you try and visualize that, it's just random. But if you sort it bottom up alphabetically, you can merge together the like stacks and actually be able to read a very complicated profile. And so that's what makes it a flame graph, is where I'm merging, the x-axis is an alphabetical stack sort to maximize merging so that you can read it. It's currently made from Perl and Svig and JavaScript, but there are a couple of D3 versions in the works, including one that we're developing at Netflix. To show you, give you an idea of where this fits into perf. So with Linux perf, we capture stacks of perf record that writes a perf.data file, and then we're dumping it with perf script and then using some open source Perl to visualize it. There are many implementations of flame graphs, by the way. My original one is not alone. These days, there's over a dozen different ones. It's a fairly simple program to write. Just the notion of you want to aggregate together frames and then emit a Svig or some rectangles. To cover interpretation of flame graphs, so here's a very simple flame graph. Colors are random in this case. The top edge shows who's running on CPU, and the width shows how much. And it's proportional. So I can see that G has run is on CPU about twice as much as I. And D is also on CPU a little bit. C is not running CPU at all, at least in this flame graph. So you just trace the top edge. That's 100% of CPU samples is the top edge. And then I can visually compare line lengths. You can go through ancestry top down. So who called G? F called G. F was called by D, and D was called by C, and so on. Just like a stack trace. And of course, you can compare the widths no matter where it is in the profile. To be more concrete, let's say I talked to the developers about reducing CPU time, and they said, we can either eliminate the B code or the H code. Which code would you rather us eliminate? I can make that decision immediately by looking at the flame graph. So B and its children are consuming about 4 times the CPU cycles as H. So just get rid of B. That'll be better. So, and of course you can mouse over and get the specific numbers, but it lets you quickly gauge where speed up, the actual speed up you'll get from making engineering choices and where engineering time is best spent. The colors are randomized by default. In my mixed mode flame graphs, I've been doing green for Java, yellow for C++, and red for system code paths. The intensity, I've just been randomizing the intensity a little bit to differentiate adjacent columns. So you can see that there are 2 columns next to each other, otherwise it looks a bit like paint. There's also differential flame graphs, where I'm taking 2 profiles, say A and B, and then I'm setting the color to be the difference between the A and B profiles. Red means you've spent more CPU time in that code path. Blue means you've spent less CPU time in that code path. We haven't automated these at Netflix yet, but I'd really like to automate these to happen every night for my microservices, so that if there was a regression, the developer could pull up the differential flame graph the next day and say, oh, we've got all this extra red stuff. We should get rid of that, because that grew. I've currently been doing this manually, like searching for planet Pluto, where we have 2 flame graphs in tabs next to each other, and you blink between them, and you're looking for where the growth is, and you go, I found it. But of course, we just use color, and color can express that as well. Search I did a quick demo of, and that's where I'm using color to show frames that have been matched by search term. There's also flame charts, which are not flame graphs, but I wanted to mention them here. Flame charts were added to Google Chrome developer tools inspired by flame graphs. They're pretty useful. but they are not flame graphs. Thank goodness they actually used a different name for differentiation. Flame charts are the passage of time. This is flipped, by the way. This is now an icicle plot. It just doesn't matter whether you do it. Some people prefer to flip it. My flame graph tool gives you minus icicle, I think, and it'll just draw it upside down, if that's your preference. But anyway, flame charts, passage of time, useful for solving issues involving a sequence of events or time-based issues. Flame graphs are good for the big picture. So you're much more guaranteed to be able to read all the function names in a flame graph, because flame charts can get a little bit messed up. Although it's not so bad in the browser, because JavaScript is single-threaded. But if you use a flame chart on like a very much multi-threaded Java application, it would not look so good. Stack tracing. So why haven't we had this forever? System profiling Java on x86. When I first tried perf-record seriously last year, this is what it looked like. This is Linux perf-record. It's supposed to be working stack traces, but each time it finds some random address, like this is junk, and unknown means it can't do the symbol mapping. And I thought, oh, well, Linux is just broken. I should try dtrace on Solaris. And so I got an instance running, and I tried dtrace, and it had exactly the same problem. And there was a bug filed in 2004 or 2005 on dtrace, which explained the problem. And it said on x86, the compiler is using the frame pointer register. Hadn't been fixed. So this is what it looks like as a flame graph. Broken Java stacks. Even though I've colored them green, they're not very useful. There should be a tower of Java, but I just see a line. They were broken because on x86, Hotspot uses the frame pointer register, RBP, as a general purpose register. This is a very common compiler optimization. Hotspot is not the only compiler to blame. Once upon a time, x86 had fewer registers, and this made sense to do so. Nowadays, it doesn't really make sense. GCC provides -f no-limit frame pointer to avoid doing this optimization. Anyone familiar with f no-limit frame pointer? So some applications are building by default with it. So Linux kernel builds by default with this, so that you can profile the kernel. But the JVM had no option. You had no -xx no-limit frame pointer in the JVM, and I really wanted it. The different ways we could fix it, we could fix frame pointer and stack logging, and then provide a mode for the JVM to say, if you turn on this flag, stop using RBP as a general purpose register. You can use a custom walker, and some other profilers have gone down that path where they'll modify the kernel, so the kernel knows how to walk Java memory space. That's very complicated, but it can be done. And the cons for that is it can cost more CPU when it's actually in use, and you're walking the user memory from kernel. There's also libunwind and dwarf, and Linux has been doing some cool things with that and perf-events. I'm not sure it's feasible with JIT. So our current preference is A, which is how to fix the broken stacks. Let's just do the equivalent of GCC's -f no-limit frame pointer and fix that. Since JDK has OpenJDK is open source, last year I started hacking on it to see if this was even possible, and found it was. And so I removed RBP from the register pools in OpenJDK and fixed the function prologues, which initialize the frame pointer register properly. And it was actually a fairly, in the end, it wasn't that many lines of code I changed. And it worked. It fixed the flame graphs. And for some time, we were running Brunden's patched OpenJDK to do things like the RxNeti versus Tomcat performance analysis. We shared a patch, and you can read the discussion about it, and it became a couple of bugs. Zoltan Mayer from Oracle took this on and completely rewrote it and made it better, and also made it, gave it an option so you could turn it on and turn it off. And so it became -xx plus preserve frame pointer. So that's been added to JDK 9 and JDK 8 update 60. And as I mentioned earlier, giving up the frame pointer register does cost a little bit of CPU, which is why it was turned off in the first place. It's not as bad as it used to be. I benchmarked it, often it's less than 1%. But you can test that if you want to be sure. Once it's fixed, when you're using, say, perf script, instead of seeing broken stacks, we now see full stacks, which looks much better, except I see the word unknown next to everything. Just because Linux perf can walk the stack trace, which is a linked list of frame pointer registers, just because it can walk it doesn't mean it knows what the method names are. But at least this is one big step closer. That's what it looks like as a flame graph. So I've just got the word unknown all over the place. One thing I do want to mention about this method of walking the stack trace is, when you walk the stack trace, what you see is exactly what's running on CPU. Java heavily inlines stuff. And when you inline stuff, you're not creating these stack frames. And so I generally see about 60% of frames are missing because the compiler has inlined all that stuff. You can turn it off if you want the full flame graphs and to get all of the stack frames out, but Java can run 80% slower. What I've found, which is pretty interesting, I've actually found it's not that important. Even though we may only be looking at 40% of the frames, you show that to a developer, and there's enough clues that you know whereabouts in your app it is. If I took JStack, and then I just elided 60% of, say, wrapper methods that didn't do very much, you probably still figure, you wrote the code, you probably still figure it out and say, okay, I know what's happening here, the other stuff has been inlined. So it hasn't been a big problem. One interesting thing is I've found, if you tweak the max inline size to relax inlining in Java so that it inlines less, we've sometimes found I've sometimes found code to run faster with less inlining. I went and got a physical box so I could do PMC analysis to test my hypothesis as to why. Anyone tell me, why would code go faster if you inline less? iCache, yes. So I tested my hypothesis, which was, if you inline really heavily, and you can turn on options in the JVM and tell you how much it's inlining and the total inline size, the method, compiled method size, you can blow out your instruction cache, your hardware instruction cache. And so by relaxing how much it's inlining, you get better, this is a hardware cache hit rate. So very good, yes. iCache, and I measured it. It didn't stick with the hypothesis. I wanted to actually measure it, make sure it's true. Symbols, fixing symbols turned out to be a much easier problem because someone had already done it. That shows what it looks like when symbols are broken and when they're not. So Linux perf already, since 2009, has had this JIT support, where if you give it this really simple text file, temp perf whatever.map, the text file just has hex address, size, and symbol name. Just stick that in there, and Linux perf will read it for translation. Great. We just need a Java agent to create that text file. And one had already been written called perf-map-agent by Johannes Rudolph, and it works. And we've been using it. So it can be loaded on demand, and it will attach to Java, dump this text file, and install it. And I use it in conjunction with Linux perf events to get the full mixed mode flame graph. There is a whole different way you can do Java symbols with Linux perf that I want to mention. It's currently being discussed on Linux kernel mailing list. It's by Stefan Aranian at Google, and that's where perf is recording. It doesn't do a snapshot of symbols, which could get a bit stale because things can move, the compiler can move things around, but it creates a time-stamped log of what the compiler is doing. And so that way, if you needed a 100% accurate symbol translation, you can use the timestamp log. It's impressive stuff. I find it pretty complicated stuff, but it's also impressive stuff. So there's more than one way to do this. That's the result. We fix the stacks, we fix the symbols, and we get all the Java method names. And I can see here we're calling into the kernel. So doing file dispatch write, system call interface, VFS write, TCP send message. Good stuff.
That stack is the machine stack. It's not like the Java code level stack, right?
Yes. So if you want to think about it, it is the machine stack. This is what's actually running on CPU. And so the only difference is we're missing some inline things from Java. And
Interpreters.
The interpreter is there. So,
well, it'll be there, but you don't know what Java put in.
Right, I don't have the arguments, so I can see the interpreter frames. But in order to know what the interpreter is working on, you have to pull out its memory, which can be done, it's just complicated. No, I have to do kernel stuff. One of the interesting things about this is you want Java to compile things. So if I do a flame graph too early, just after starting my application, if I do it in the first 10 seconds, and it's mostly interpreter, I can't, there's less information. You just get interpreter is running. It's like, I don't know what that means. I don't know what the interpreter is thinking about. You actually have to wait for your application to warm up like a minute or 2 minutes. Then get the machine code stacks, because as part of warming up, the interpreter hits the threshold of 10,000 invocations, and it will then compile that up, and now it's machine code that can be profiled. So yeah, it's more interesting internals of how this all works, but you can't do flame graphs. You have to have a little bit of patience. You have to wait a minute or two to give the compiler a chance to be running machine code so that you can profile it. Now, I had instructions on the Netflix tech blog, which you can refer to. I'll just breeze through them quickly here to give you a feeling for it. So, JDK 8 update 60 or better. Perf-map-agent is the one we're using at the moment, and that will dump do a symbol dump. I should mention that these are all unsupported. Netflix doesn't sell Java support. We're just sharing how we actually do this. And so I know some of this software like perf-map-agent comes with its own warnings of, I'm not a C programmer, and you need to know what you're doing if you are willing to run this. So do run it in a test environment. So perf-map-agent, that does the symbol translation. You do need to preserve frame pointer running so that the stacks can be walked. Profiling Java, like the commands I had earlier, I can profile everything on the system, my NSA, or I can profile an individual process ID. Dump symbols out using perf-map-agent. It gets a bit tricky when it comes to user ID and ownerships. If you've played with this stuff, and you need to run perf as root, and you need to run this as the same owner as Java. The first time you try this and you stumble into all this weirdness, you'll want to shell script it. And you'll want to, it's like, I never want to type this in the command line again. I never want to type chown user such and such. And so perf-map-agent came with its own helpers. I've written my own helper, which is also unsupported JMap, so I'm sure you'll write your own. So you end up automating that step where it dumps the symbols out, and then you use flame graph software, which could be mine, it could be someone else's, to generate the mixed mode flame graph. All of those steps are on that Java and Flames Netflix tech blog. It's not really a lot of steps, it's all open source code. If you do it a few times, you'll want to automate it, and it can be automated. And that's what we've been doing at Netflix for Vector, which is open source. This is our real-time instance analysis tool, which we can point to an instance. And if we see CPU utilization is high, we can then give us a flame graph, and it will then go and collect that and display it. That's on github.com Netflix Vector. The current implementation of it was using my Perl software to do flame graphs, but we've been developing D3 flame graphs as part of Vector. And just to give you a quick peek of why that's interesting, this code is on GitHub as well. So here's one of my old profiles, flame graph profiles, just as like a test card. And with D3, we have interactivity. Wow. It's like there should be sound effects. Whoop, 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 whoop. I can do this all day. So it's fun. So that's going to be the future of flame graphs. And just the interactivity is that sells it for me. So I'm afraid my old Perl version might have to be retired. But one of the more interesting things we can do with interactivity is I can then create more toggles for working with the data. For example, one nuisance step that I do with my Perl version is, you can tell the flame graph I'm merging into bottom. What if you want to do a leaf merge instead of a root merge? So what if your Java profile, you kept hitting the same lock code path, but it's scattered all over the place? So I can use search to add it up, but wouldn't it be good to split the merge order and merge at the top instead of the bottom? Just as a different way to process the data. That's one of the many things we want to do with the D3 version. Just to give you a button to flip how it gets merged, interactively move it around, should be really cool.
So from a central node also, for example?
Yeah, we could do a central node as well. Like to change the point of merging. Different ways to process that data. It's just too cumbersome to do it for my code program, and D3 is pretty well suited for that. And it's all open source, and you can contribute if you like. In fact, there's more than one D3 version people are working on. There's multiple ones. Advanced analysis I want to finish with is, that's great. So with, say, Linux perf-events and perf-map-agent, and with preserved frame pointer, I can do complete CPU profiles. But what else can I do? And so Linux perf-events is a really capable system profiler, and I've got a picture here showing what it can do. So dynamic tracing, trace points, PMCs. What's amazing is we can now look at any of these events with Java stacks. So previously, if you'd looked at this stuff and thought, oh, that's really boring, like, all right, fine, I'm doing kernel scheduler stuff, but I need to see Java, I need my Java stack context to make sense of it. Well, now we can do it. It has to be in synchronous Java context. And to tell you what that means is, let's say I want to know in my Java code, who is issuing disk I/O. That should be okay. That should be synchronous context. If it's a direct read, if it's a synchronous write, if it's a page fault. If I want to know who in my Java code is doing disk completion interrupts, that's not going to work. When a disk I/O completes, Java's long gone. It's just the kernel that's running on CPU. It's probably the idle thread. So if you try and capture the Java stack on the completion interrupts, you won't find it. What about disk I/O requests triggered by some asynchronous task? So let's say I'm reading a file sequentially, the file system on the completion interrupt then says, you keep reading the same file in a row, I'm going to trigger a read ahead. Well, Java could be nowhere on the scene. The file system's decided to do that. So if you try and look at this Java stack, it won't be there. It would just be the kernel. There are workarounds, so you can record the Java stack and associate it around and connect the dots. But it's just something you have to mentally think about when you do the advanced things is it synchronous or not? TCP send message should be synchronous when you buffer it. TCP receive message shouldn't be synchronous. Like that could just happen anytime. Like a packet could just arrive. And your Java application won't be on CPU. So if you can think along those lines, you can do a lot of really cool things. Here's page fault flame graphs. If you're running top and you keep seeing resident set size grow, and we had one of these recently, where we know it's basically a memory leak, and it grows until the killer comes along. Well, the kernel process that grows that column, res, is a page fault, because the kernel uses non-demand allocator. So virtual memory gets allocated by malloc immediately, but when you first touch that memory page with a write, it then does a fault because the kernel had lied to you earlier, and now the truth is revealed, and it has to go and map an actual page of memory in. You can grab the kernel's, the Java stack at that point, and it should be synchronous, to show who wrote to memory to cause the growth. And so I whipped up an example yesterday to show that it does work, and I was finding most of my memory growth was from epoll wait, which is interesting, and also GC shuffling things around, which is not too surprising. Will be much more interesting if you do this on a slow-running memory leak. Context switches, same thing. When the kernel decides to pull you off CPU, or if Java blocks for any reason, whether it's locks or I/O or if it's doing sleep, grab your stack trace. Why are you sleeping? Why are you just running forever? Keep running, burning CPU cycles and completing my task. Why would you go to sleep on the job? And so doing context switches and stack traces. I actually did this earlier in the year because we're trying to understand why RxDD was more efficient than Tomcat. And RxDD, most of the time, when it went off CPU, it was because it was waiting for work. And then there was some overhead with futex or locks. And then Tomcat was much, much messier. And so it was blocking because of syspoll, which is a less efficient way of waiting for work than epoll. And all sorts of other things as well, like lock intention was showing up. Disk I/O requests, I mentioned. I ran this on an application that was doing no disk I/O, and to my surprise, I captured a stack trace, and I thought, well, this shouldn't have happened. Something must be wrong. And it's showing that we were doing disk I/O from GC. And also my Java thread, we were triggering page faults. Page faults was doing disk I/O. Now I had a look at that instance, and I didn't know it, but that instance had been swapped out. The instance had run out of memory, and a swap device was configured, which is not the norm. It's not how we normally run things. But it was then paging it back in, swapping it back in, and that was causing the disk I/O. So, nice discovery. TCP events. So here, just as an example of using dynamic tracing, where I'm instrumenting TCP send message, and I want to copy and paste the whole command. It should be probe send message, sleep for 1 second, and then print it out. And I can see the full stack from start thread, JVM, Java, and the kernel to the point where we're doing a TCP send message. And so this is really boring because it's all one path. But you may have an application where you don't know, why am I doing TCP stuff? Why am I doing TCP connections? Just show me the code paths that get to it. I have to be really careful about tracing TCP send message because it's really frequent. And so I was doing a sleep once, I was only capturing 1 second of this output. But it can be done, and that's the important part. CPU cache misses is just another interesting advanced example, and that's where I'm using the performance monitoring counter capabilities of Linux perf events. I'm instrumenting last level cache loads, that's the hardware cache. Every 10,000, go and capture a stack trace. And so now I've got a flame graph. This is the first time I did this, by the way, so I'm excited it worked. Now I've got a flame graph that shows these are the code paths that led to you doing memory I/O, which may be interesting as a developer because ideally, as much as possible, your code will cache in the level 1 and level 2 caches. And so this shows where it didn't work, and it had to go all the way out past the level 3 cache into main memory. And so I can navigate through that and then look for areas of optimization.
Do you find that this works now on virtualized systems? You're running on Amazon a lot, or do you need
yes.
environmental?
I can't run this on Zen yet. So I ran this on a physical system just to have a nice example. I'd love to run this within the Zen guest. So the problem with Zen guests is when you virtualize, it's hard work. I've worked on virtualization technology. As an engineer, you have to virtualize all sorts of stuff. One of them is the PMCs. And different hypervisors are at different levels of support for PMCs. Zen currently does not export the PMCs to guests, but it is technically possible. And so I would like in the future for Zen guests, which is what Amazon EC2 give you, to provide PMC support. Anyone in the room on Amazon EC2? There you go, so I can tease you. Wouldn't it be nice if we could do this? So you can talk to your sales rep. So no, I'm sure this isn't something that I think you'll never have, because you can do this. You can get this stuff to be exported out through a hypervisor. So it's just something that one day I hope will appear as a feature. I was actually playing around with MSRs, model-specific registers, to figure out low-level things on Zen guests, because they were exposed, and PMCs currently are not. The very last example I have, back to a mixed-mode CPI Flame Graph. This one is showing a Vertex profile that I was doing a benchmark study of earlier in the year. So I can see my JVM, Java, and kernel code, and it's all proportional. What else can we do with colors that's interesting? Now I'm decorating it with cycles per instruction. If you get into the CPU performance counters, CPI, or IPC, which is the same thing, inverted, is the first thing you hit up. It's like the load average of understanding CPUs. It's really dumb, but it kind of works. Cycles per instruction, if your cycles per instruction is high, like it's 5.0, it means you've got memory slowdown or resource slowdown. You're doing a lot of cycles to retire one instruction. If your cycles per instruction is very low, like it's 0.33. It can go less than 1 because of pipelining. We have a multi-way instruction decode and execution, parallel execution. If your CPI is low, you know you're retiring instructions really quickly. Oh, I have a new version of Java available. Why, thank you. It's Java 8 updated. Oh, it's update 65, which means it comes with a preserved frame pointer. I definitely want this, and you do too. So, yes, remind me later because that will be awesome. So CPI Flame Graph, it's decorated this with colors to show me red is where I'm burning through instructions a lot. Blue is where I'm waiting on memory more. And so as a developer, that lets you change your corrective action. So if I found there was a lot of deep blue, it might tell me that maybe I should change my the objects and how much memory I was doing, like investigate zero copy, just to reduce how many loads and stores that code path has to do. If it was red, you have a different course of action. It's, why am I just burning through lots of instructions? Is it order n squared? Can I make it order n? And so that information is really useful. Decorating the flame graph. So these are the CPU cycles, but the color gives you more information about why it's that way. What are the CPUs doing at a low level? At the end of my talk, and I will share the slides on SlideShare, I have all links to various things, so you can run these yourself. And that's my talk. Thank you very much. Now we have time for a few questions, and there's also, you can also find me afterwards at the conference to ask me questions. And I've also got contact details there. If you need to run out really quickly to get the next session, I understand. Yes?
Just a quick question. The perf-map generator agent thing, I'm assuming that the overhead for that is extremely low. It's basically just a compiler log.
Yeah, I mean, the overhead for perf-map-agent was the overhead, which is the symbol thing. It used to be always on, so you have to load it on Java Startup. And I wasn't too comfortable with that, but Johan has changed it so that it was on demand. So I can go to a Netflix instance that's never run this before. It's having a production issue right now, and I can load it without restarting Java and then capture a log. The overhead, we do need to, so it's on demand, which is really good. The overhead is a little bit annoying. It can take like 2 or 3 seconds, between 1 and 5 seconds of CPU time. Just if it's a really big, like complicated application, just to dump all the symbols out. That is a problem for us because our instances are quite sensitive. If you perturb an instance, the Netflix environment is fault tolerant. It can move traffic away immediately. And so if I perturb an instance too much through an observation tool, it's like, hey, the performance problem is gone. In fact, all the load is gone as well, because it's just moved it elsewhere. So I would like to make that overhead a bit less, where it's dumping the symbols.
So by on demand, it just basically gives you a snapshot in time of the entire symbol table on that JVM.
Right, and it could change. So if you did a 60-second profile, the symbols could have changed a little bit from start to end. You could do a before and after snapshot and then highlight the differences. Or you could go down Google's path where they're doing the always-on symbol log so that they can have all the timestamps for every single compilation. But then that costs overhead to always be dumping what the compiler is doing. File system overhead, CPU overhead.
But potentially less work, right? Because it only does the dump.
Potentially less work, yes. If you've got it turned on from the start. But how would we do that at Netflix? See, most of the time, we have tens of thousands of instances. Which one is going to have a performance issue? For that approach, we'd have to turn it on all of them. I'd much rather the on-demand approach where it's only this one has an instance, only turn it on. I might pay for 3 seconds of CPU time, but it's better than having it turned on everywhere.
Eventually keeping being always on, the mapping file could get potentially very large.
Mapping file could get very large. We had that problem
larger than the local disk.
We had that problem with Node.js because its mapping file was getting into the gigabytes, and so I filed bugs and we were trimming it. But yeah, it could get stupid. Yes.
Have you experimented with sampling?
Have I?
Try lower sampling. Like 99
99 sounds excessively high. I used to use 999 all the time, or 997. I recently wrote on my hard interrupt profiling tools so that I could measure the overhead of doing, in soft interrupt profiling tools, so I can measure the overhead of it. And at 999 hertz, you can actually measure it. At 99 hertz, it's really optimized. It's pretty low. But
Depends on the OS.
depends on the OS.
And how many threads you got.
Oh, I mean,
And-
like, what if you're running like 1 hertz?
So here's my answer. I'm fine going lower. I'm fine going down to 9 hertz. The problem is I don't want to go for longer. If you're only going to do one symbol snapshot, I don't want to wait 5 minutes at 9 hertz and then do a symbol snapshot because the likelihood you've had symbol churn is higher. Unless you want to do before and after symbol snapshots or use Google's approach of the always dumping symbol changes,
But it's not been my experience.
which has not been your experience.
No, my experience is the lower sensitivity
It depends on the profile. JStack and lots of other profiles can hurt things at low rates. But you should try Linux perf events with just the frame pointer based walking. It's really cheap. On LKML, Analdo, who's one of the main authors, it was Andy Klein from Intel. He just halved some of the time. It was measuring in nanoseconds. It's like, hey, I just made it go like 40 nanoseconds instead of 80. It's like, wow, you guys are crazy. But like that particular profile has had a lot of optimizations. But of course, measure it. It'll always be good to think about it.
For most of the graphs you showed, it was over like 30 seconds or lower. Have you generated these graphs from like longer data sets, like into the hours?
I could, but then if I didn't, no, I haven't. There's a few problems. So perf dumps to a file on disk, and that's going to get big if you do it for hours. I'd have to reduce the sample rate. I could have symbol churn as well because the way it's doing these snapshots of symbols.
I'm just more curious about like how the visualization
Yes.
represents your code set.
Yeah. What
for a long period.
we do want to do is capture basically rolling flame graphs. And with D3 and animations, you can imagine like a play button where the flame graph changes over time and shows you like this is how it changed over the last hour. Because Java does not have at least in my experience, Java does not run steadily. So you have GC runs and other activities can run and change the profile second to second, minute to minute. So doing it over time would be really interesting. I have not done it yet, but I would like we're going to have to really think about symbols, but to do, say, a 1 minute flame graph every 5 minutes, and then chain them together and do an animation. It would be pretty cool. Yes?
So all the graphs you showed so far had sort of a same depth to them.
Oh, yeah.
What happens when you go into one of those, CDI, spraying all those, where you have a 376 deep stack?
Yeah, and the stats I showed weren't too crazy. I did profiling in production of Groovy, and the stack trace was just crazy. And we still figured it out. So with these really long stacks, which can be 300, 400 frames, there are repetitions. Someone already wrote a filter for my flame graphs that will fold similar identical frames. If it doesn't do it already, it should identify like a repeated 3 frames, because that's what was happening with Groovy. It's like the same 3 frames over and over and over. So I think we just need to do some munging of that data and collapse it down with flame graphs. Another community that's had a big problem with that is Ruby on Rails. And so their flame graphs were just crazy, like 1,000 frames. And so what they were doing was, instead of printing a frame and putting the text inside it, they were printing a single line, like a single line of pixels, and then just stacking all the pixels. And it's like, all right, but we made it fit on the screen, and then you zoom in and see the detail. So. Yes?
I was wondering, a complete different direction. There are a few commercial APM tools, and you kind of this poster story for App Dynamics. Do you still use this? I mean, from what I got from you, you're basically more focused on this and on this clicky tree thingy. How do you do it at Netflix right now? Did you completely drop this off? You just used it with your vector visualization for monitoring?
Yeah, so Netflix in the past have used lots of different things. We also have lots of microservices, and so an application group may use their own profiler. I did have a picture in here showing the base AMI, and the base AMI currently, the only profilers in it is the Linux perf events, Vector, and Atlas. And so we don't have any third-party stuff in the base AMI. If you have a buddy who works at Netflix and says, oh, but we're using this, it's because freedom and responsibility, teams can, if it makes sense for a team to use something, they can do that. But standard, the base AMI, we don't have anything right now.
This is also, you're using this more as a drill down tool rather than a continuous monitoring, right? Or do you do both?
More of a drill down tool for the continuous monitoring. I don't know if there's another session in here, but I think we should end it now. But thank you for showing up, and you're welcome to ask me questions after.